training compute is kind of like the engine. There's horsepower of the engine. So you want to try to do the best on that, and then so how efficiently do you use that training compute, and how efficiently do you do the inference, the use of the AI? So obviously that comes down to human talent, and then what unique access to data do you have? That's also plays a role.
You think Twitter data will be useful?
Yeah, I mean, I think most of the leading AI companies have already scraped all the Twitter data. Not I think they have. So I don't know, on a go forward basis, what's useful is the fact that it's up to the second.
Yes.
That's because it's hard for them to scrape in real time. So there's an immediacy advantage that Grok has already. I think with Tesla and the real-time video coming from several million cars, ultimately tens of millions of cars, with Optimus, there might be hundreds of millions of Optimus robots, maybe billions, learning a tremendous amount from the real world. That's the biggest source of data. I think ultimately is sort of Optimus. Optimus is going to be the biggest source of data
because
reality scales. Reality scales to the scale of reality. It's actually humbling to see how little data humans have actually been able to accumulate. Really, if you say how many trillions of usable tokens have humans generated, where on a non-duplicative, like discounting spam and repetitive stuff, it's not a huge number. You run out pretty quickly.
And Optimus can go, so Tesla cars unfortunately have to stay on the road. Optimus robot can go anywhere. There's more reality off the road and go off road.
I mean, like the Optimus robot can pick up the cup and see, did it pick up the cup in the right way? Did it, say, pour water in the cup? Did the water go in the cup or not go in the cup? Did it spill water or not?
Yeah.
Simple stuff like that. I mean, but it can do that at scale times a billion, so generate useful data from reality. So cause and effect stuff.
What do you think it takes to get to mass production of humanoid robots like that?
It's the same as cars, really. I mean, global capacity for vehicles is about 100 million a year. And it could be higher. It's just that the demand is on the order of 100 million a year. And then there's roughly 2 billion vehicles that are in use in some way. So, which makes sense. Like the life of a vehicle is about 20 years. So at steady state, you can have 100 million vehicles produced a year with a 2 billion vehicle fleet, roughly. Now, for humanoid robots, the utility is much greater. So my guess is humanoid robots are more like at a billion plus per year.
But, until you came along and started building Optimus, it was thought to be an extremely difficult problem. I mean, it is an extremely difficult problem.
So it's no walk in the park. I mean, Optimus currently would struggle to walk in the park. I mean, it can walk in a park. The park is not too difficult, but it will be able to walk over a wide range of terrain.
Yeah, and pick up objects.
Yeah. It can already do that.
But like all kinds of objects.
Yeah.
All foreign objects. I mean, pouring water in a cup is not trivial. Because then if you don't know anything about the container, it could be all kinds of containers.
Yeah. There's going to be an immense amount of engineering just going into the hand.
Yeah.
The hand might be close to half of all the engineering in Optimus. From an electromechanical standpoint, the hand is probably roughly half of the engineering.
But so much of the intelligence of humans goes into what we do with our hands.
Yeah.
There's the manipulation of the world, manipulation of objects in the world, intelligent, safe manipulation of objects in the world. Yeah.
Yeah. I mean, you start really thinking about your hand and how it works.
I do it all the time.
The sensory and control homunculus is, we have humongous hands.
Yeah.
So, I mean, like your hands, the actuators, the muscles of your hand are almost overwhelmingly in your forearm.
Mm-hmm.
So your forearm has the muscles that actually control your hand. There's a few small muscles in the hand itself, but your hand is really like a skeleton meat puppet, and with cables so the muscles that control your fingers are in your forearm, and they go through the carpal tunnel, which is that you've got a little collection of bones and a tiny tunnel that these cables, the tendons, go through, and those tendons are mostly what move your hands.
And something like those tendons has to be re-engineered into the Optimus in order to do all that kind of stuff.
Yeah, so like the current Optimus, we tried putting the actuators in the hand itself, but then you sort of end up having these like
giant hands.
Yeah, giant hands that look weird.
Yeah,
and then they don't actually have enough degrees of freedom or enough strength. Mm-hmm. So then you realize, oh, okay, that's why you got to put the actuators in the forearm, and just like a human, you got to run cables through a narrow tunnel to operate the fingers. And then there's also a reason for not having all the fingers the same length. So it wouldn't be expensive from an energy or evolutionary standpoint to have all your fingers be the same length. So why aren't they the same length?
Yeah, why not?
Because it's actually better to have different lengths. Your dexterity is better if you've got fingers of different length. There are more things you can do, and your dexterity is actually better if your fingers are of different length. Like there's a reason we've got a little finger. Like why not have a little finger that's bigger?
Yeah,
because it allows you to it helps you with fine motor skills.
This little finger helps?
It does. If you lost your little finger, you'd have noticeably less dexterity.
So as you're figuring out this problem, you have to also figure out a way to do it so you can mass manufacture it. So it's to be as simple as possible. It's
actually going to be quite complicated. The as possible part it's quite a high bar. If you want to have a humanoid robot that can do things that a human can do, it's a very high bar. So our new arm has 22 degrees of freedom instead of 11, and has the actuators in the forearm. And these all the actuators are designed from scratch, from physics first principles. The sensors are all designed from scratch, and we'll continue to put a tremendous amount of engineering effort into improving the hand. Like the hand, by hand I mean like the entire forearm from elbow forward. Mm-hmm. Is really the hand. So that's incredibly difficult engineering, actually. and so the simplest possible version of a humanoid robot that can do even most, perhaps not all, of what a human can do is actually still very complicated. It's not simple. It's very difficult.